In this video, we're going to talk about SN2 reactions. This chapter is largely about the reactions of alkyl halides, and those reactions fall into two categories. Substitution reactions, where we replace the alkyl halide with another nucleophile, and elimination reactions, where we remove the halogen and a neighboring hydrogen atom to form an alkene. An SN2 reaction is an example of a substitution reaction, and we'll talk about elimination reactions in subsequent videos. So before we talk more specifically about SN2 reactions, we need to talk a little bit about alkyl halide structure and some terminology that we use. So to specify the carbons in an alkyl halide, the carbon that is directly attached to the halogen is denoted as the alpha carbon. Carbons that are one away from the alpha carbon are called beta, and then if you want two away would be gamma. Now the amount of branching on the alpha carbon also has a big impact on the reactivity of these alkyl halides. And so some terminology that we've already used for carbocations. If I want to talk about how many other carbons are attached to the alpha carbon, if there's one other carbon, that would be primary. If there's two carbons attached to the alpha carbon, it would be secondary. And then if there are three carbons attached to the alpha carbon, that would be tertiary. Now there are two possible mechanisms for a substitution reaction. We can have either a stepwise or a concerted mechanism. In a stepwise mechanism, first we have the loss of a leaving group, and then the resulting carbocation gets attacked by a nucleophile. Now this is actually an SN1 reaction, and we'll discuss it later. An SN2 reaction is the concerted mechanism, which we'll talk about on the next slide. So in a concerted mechanism, the loss of the leaving group and the attack of the nucleophile actually happens at the same time. And so that's what we mean by concerted. Both steps happen at the same time. And this is in fact what happens in an SN2 reaction, is going to be the subject of the rest of this video. So I think it's helpful to see where the name SN2 comes from. So the S comes from the fact that this is a substitution reaction. The N comes from the fact that it involves nucleophilic attack, and the 2 comes from the fact that this is a bimolecular reaction, meaning it depends on the concentration of both the nucleophile and the alkyl halide. Now it's important to talk about the kinetics of an SN2 reaction. If you remember from general chemistry, one of the things that we talked about in the kinetics chapter was mechanisms. And we said that if we have an elementary step in a mechanism, we can determine the rate law from that, and that however many things are colliding or reacting in that specific step will allow us to write the rate law. And so in an SN2 reaction, this elementary step involves both the nucleophile and the alkyl halide. And oftentimes we refer to the alkyl halide as the substrate, right? It's sort of the compound that's being reacted upon. And so in this elementary step, it involves one nucleophile and one alkyl halide, or one substrate. And so the rate law for this step is rate is equal to the rate constant times the concentration of the nucleophile times the concentration of the substrate. And so this reaction, or this elementary step, is second order overall, and that's where the bimolecular, or the 2, comes from in the SN2 name. Another really important feature of SN2 reactions is the stereochemistry, and the fact that SN2 reactions involve what's called a backside attack and an inversion of configuration. And so what we mean by backside attack is if the halogen is on this side of the substrate, the nucleophile actually attacks from the other side. So the lone pair on the nucleophile attacks the back end of the carbon atom. And then this causes sort of like an umbrella sort of flipping open the wrong way, right? Sort of the curvature, right? It's going like this, right? And then the groups are sort of pointed in the other direction when the bromine comes off. And as a result of that, if we have a chiral center, if it was S in the reactant, then the configuration is going to be R in the products, and vice versa. If it started out as R, it would have ended up as S because of this backside attack and the inversion of configuration. I think it's helpful to think about what the transition state looks like for an SN2 reaction. So remember that in an SN2 reaction, we have backside attack. So the nucleophile attacks from the opposite side of the carbon atom that the halogen resides on, right? And so it does not attack it via a front side attack. And there's sort of two things going on in this concerted mechanism, right? We're making a bond between the nucleophile and the carbon atom, and we're breaking the bond between the leaving group and the carbon atom. And so the transition state needs to reflect sort of both of these processes happening at the same time. And so the way we imagine the transition state, and I don't have enough room here, so I'm actually going to draw the transition state down here to the right. And just a note on terminology, a symbol that we often use to represent transition states is this, what's called a double dagger. And so when we put something in brackets and put a double dagger in the upper right-hand corner, we're saying this is a transition state. And so the way we typically imagine the transition state is that it's halfway between the inversion of configuration. So we sort of have a situation where, in this case, right, we've sort of got the ethyl going down, and then the methyl group and the hydrogen, in this case, are sort of planar, right? We're sort of in the middle of flipping our umbrella inside out. And then we often use dashed lines to represent, right, this isn't a full bond anymore, right, but we're breaking the bond with the bromine, and then we're in the process of making the bond with our nucleophile. All right, here's another example of an SN2 reaction involving a different substrate and nucleophile, but you can see the transition state has a similar structure to the one that we drew before, where the other substituents are sort of in a planar position, right, in the process of breaking the bond with the leaving group and making the bond with the nucleophile. And remember that the transition state is the highest point on these reaction energy diagrams. I mentioned in a previous slide that the number of substituents on the alpha carbon of the alkyl halide plays an important role in how reactive that alkyl halide is going to be. And it turns out the more substituents we have on the alkyl halide, the less reactive it is. And so tertiary alkyl halides are generally unreactive, whereas methyl alkyl halides are the most reactive. And this basically comes down to steric hindrance, right? The more bulky substituents we have on the alpha carbon, the harder it is for that nucleophile to get in and actually react. And so to make this a little bit more qualitative, we've got some relative rates here. And so you can see the effect on alpha substituents. So if we are measuring the rates relative to having a primary alkyl halide, right, we can see that the methyl alkyl halide reacts much more quickly, right? And as we go to secondary and tertiary alkyl halides, right, the reactivity falls off significantly, right? Not only do substituents on the alpha carbon affect the rate, but substituents on the beta carbons also affect the rates. And so, right, this is my alpha carbon, this is the beta carbon, and so if I start adding substituents to the beta carbon, that also slows the reaction down. And that's also for steric reasons, right? The beta carbon is a little bit further away, so its effects are less, but still the more stuff we have coming off that beta carbon, the more steric hindrance there is, and the harder it is for the nucleophile to get in and attack that alpha carbon to undergo the substitution reaction. Okay, and so when reactions become slower, remember that the rate of reaction depends on the height of the activation energy, right? And so for an SN2 reaction with a methyl substrate versus a primary substrate, which should be slower, versus a secondary substrate, which should be even slower, right? The activation energy increases as the reaction slows down. Okay, I'd like to finish this video with just a couple examples. And so in this example, we're given a couple different possible SN2 reactions, and we want to know which one would have the fastest rate. And so we're comparing a secondary alkyl halide to a primary alkyl halide to a methyl alkyl halide, right? And so the more substituents we have coming off that alpha carbon, the harder it is for that nucleophile to get in and attack that alpha carbon. And so we would expect the secondary alkyl halide to be the slowest, and so the fastest is going to be the one with the least steric hindrance, and that would be the reaction where the substrate is a methyl alkyl halide. Okay, in this example, we want to draw the SN2 reaction between S2-chloropentane and this nucleophile. And we also want to show the mechanism using curved arrows. Right, now remember from the acid-base chapter, when we have sodium in a compound, right, that sodium is going to be a counter ion, right? And so my nucleophile is really this species. All right, so if we start by drawing S2-chloropentane, all right, so there's my pentane, and then I need to have the chlorine coming off carbon 2, and so I'm going to number it as 1, 2, and I need it to be S. And so what I typically do is say, okay, let me put in the chlorine, and I'll put it in as a wedge, and then we'll check and see if in fact this is S2-chloropentane, and if it's not, right, if I figure out that that's R, right, then I just need to change my wedge into a dash. Right, and so when I assign priorities to determine the configuration, I think the chlorine is going to be 1. These two carbons are tied, right, but this has 3 H's, this has a carbon and 2 H's, so this would be the second priority and the third priority. Then, of course, I have a hydrogen in the back that I'm not showing that's going to be fourth priority. And so when I go 1, 2, 3, right, I think I have drawn the S configuration, right? If I'd wanted R, then at this point I'd need to change the wedge into a dash. But because I want S, I think I'm good. All right, and I'm going to go ahead and put the lone pairs on the chlorine, and then I'm going to react that with my with my nucleophile. Right, and so the mechanism, right, is going to be that one of the lone pairs on my nucleophile attacks the alpha carbon, and then at the same time, right, the carbon-chlorine bond is going to become a lone pair on that chlorine as it turns into a leaving group. And so now, for my products, right, now the sulfur is going to be attached, or the SH is going to be attached to that carbon 2, but remember the inversion of configuration, right? So I started out with the S, right, and now I need to have the R. So that SH is going to be, instead of a wedge, I'm going to want to draw that as a dash, and then we're going to have our chlorine coming off. Okay, and for our last video, we want to draw the transition state for this reaction that we drew the reaction for on the previous slide. And so, right, I'm going to have my carbon that's being attacked in the center, right? The chlorine is going to be leaving. My nucleophile is going to be forming that bond, and I think I didn't do this on the previous transition state, but I think it's nice to show, right, that this is going to be partially negative, and this guy is going to be partially negative because, right, in the reactants, this had the full negative charge, and the product this had the full negative charge. So in the transition state, right, we're sort of in the process of transferring that electron density, and then I'm going to have a methyl group and the hydrogen, and then we're going to have, right, sort of the 3 carbons, right? So in my 2-chloropentane, right, 1, 2, 3, 4, 5. And so to finish this off, we often like to put the transition states in brackets, and then we might put the double dagger to indicate that this is a transition state.